Hello, good afternoon, everyone. Can you hear me? Yes, Xiaoting. Thank you. Okay. So for last week, we have completed the first chapter, Introduction to Renewable Energy, and now we will skip the XRD chapter first. Okay, and then we'll start with this chapter three, solar energy. Part one. There are four parts in this chapter. Now we're going to learn about the part one, just a very basic introduction about the solar energy. Okay. So first of all, what you know about solar energy? So in general, solar energy is originated with the thermonuclear fusion reaction occurring in the sun, which is a fusion of four hydrogen atoms into one helium atom. And this thermonuclear fusion, you can see that hydrogen and helium is also available on the Earth. But on the Earth, we do not able to achieve thermonuclear fusion like in the sun. Okay, this because any idea why? Why we cannot achieve thermonuclear fusion in on Earth? It's only happen on the sun. Hydrogen and helium we also have a lot on Earth, but we never have the thermonuclear fusion never happened. Okay, the reason is to achieve this thermonuclear fusion, there are three necessary conditions. First, you need to have very high temperature, which is very hot enough to allow the iron to overcome the Coulomb barrier. Okay, because the nuclear of the atom itself have some kind of repulsive force. Okay, so you need to have the high temperature so that they have enough energy to overcome this repulsive force between the atom nuclear. Okay, and the temperature should be at least 100 million degrees Celsius. Okay, so in general, in the normal circumference, we will never achieve 100 million degrees Celsius. Okay, and then the second condition is that iron have to be close enough or confined together in close proximity. They have to close together so that they can have the chemical reaction. Okay, so how to make them close enough? Then you need to have a lot of atom in a very small area or very high density. Okay, high density, so that you only can achieve this close proximity. Third, they need to have high temperature and close proximity for long enough duration. The duration must be long enough to avoid the plasma cooling. This is because something like this. You want to have a chemical reaction between two bodies. Then you put them together. You force them as close as each other together. But for 1 second or 1 millisecond may not be enough. So you have to hold them at that position for long enough. Then they only can have this chemical reaction. Okay. So for thermonuclear fusion to happen, you need to have these three criteria: temperature, the distance must be close enough, the third must be the duration must be long enough, or we can link these to pressure. You need to brush them together at a very long period. Okay, of course it will not happen naturally on Earth, but we actually try to make the artificial sun. The first to successfully make this artificial sun is Korea. They make artificial sun. They achieve this 100 million degrees Celsius temperature. I can't remember for maybe 30 seconds or 60 seconds, something like this. Okay, and then after this, China break the record again at the same temperature, but it can hold the temperature for around 2 minutes. Okay, I think that is the world record they have, Korea and China. They make the record. But the actual purpose of this, I also not really sure about this. What can they do about this? Maybe just to find to make an artificial sun in the future. Okay, but they have a very huge lab to do this kind of the artificial sun. Okay, and solar energy is represent the entire. Was blocked by the figure. Never mind. It represents entire electromagnetic radiation. Okay, it means that it is have a spectrum, and this spectrum including the X-ray, UV, visible light, infrared, microwave, and radio wave, all kind of electromagnetic wave. Okay, a package they come together. Okay, and you can see that in this solar energy, we actually have the sunlight. Sorry, we actually have the X-ray, but we never receive X-ray on the Earth's surface. And you try to imagine, X-ray is very dangerous to us. Okay, it will kill our body cell. Okay, so if you long time exposure to X-ray, then it definitely will kill you. But luckily, the atmosphere of the Earth already filtered out all the X-ray. Okay, but why the other waves still able to reach the Earth's surface, but X-ray not? Okay, you can look in this way on the graph on the right hand. Sorry, wait a minute. Okay, if you look on the graph on the right hand side, what's how to differ between different type of wave here, according to the wavelength. Okay, X-ray is the shortest wavelength. Okay, and then followed by UV, visible light, infrared, microwave, and radio wave. Infrared radiation is mostly, we can refer it to the thermal radiation. Okay, heat. Okay, radio wave is what we know lah. We transfer the signal through radio wave. And microwave what we use lah in our house to heat up your food or what. Okay, so X-ray has the shortest wavelength, and at the same time it has the highest energy. Why it has the highest energy here? Okay, maybe we can explain this way. This is a X-ray, and this is a radio wave. Okay, so we can see that the wavelength actually is much shorter. So in a second of time, of 1 second, it will vibrate more cycle compared to the radio wave. So in other words, it needs more energy to move. Okay, so that in 1 second it already move maybe 20 cycle, but this radio wave only move 1 cycle. So that it has a very high density of energy. That's why it is very dangerous. Radio wave is almost harmful to the human because the energy content in the radio wave is too low. Okay, so X-ray, in other words, is very dangerous, very high density. But why this high density wave will never reach the Earth's surface? You can imagine that between the Earth's surface and outside the atmosphere thickness is around 50 kilometer thickness. Okay, so let's say the radio wave, it can easily pass through the atmosphere. Okay, you can see that the wavelength of radio wave is 1 km. Okay, this is 1 km. So in other words, in order to travel 1 km, this radio wave only complete 1 cycle. But how about X-ray? You can see that the wavelength is about, I think about lower than 200 nanometer. Okay, so to complete 1 kilometer length, it need to be something like this. How many cycles is already completed? And every cycle, it will need to overcome the resistance from the atmosphere. Okay, so it means that it will need to overcome more resistance than the radio wave. So in other words, the energy will lose faster because move too fast. Something like you drive your car. If you drive faster, you feel that the air resistance outside will be stronger. Okay, and also the distance travel here, because they move up too many times, so that the energy will be completely drained out very fast. So it will never reach the Earth's surface. Then the rest, UV light, visible light, and others, all will reach the Earth's surface. UV light is optional. In some of the case, the atmosphere will completely filter out, but some of the case it still reach the Earth's surface. Okay, but X-ray never reach the Earth's surface. It should be quite lucky. It's not really reach the Earth's surface, or it should be killed. Okay. And what is the solar and oxygen? Okay, sun radiates energy at the rate of 3.9 times 10 power 26 watt. This is a very big value. So maybe you are not able to imagine, but maybe just it's a value. This 3.9 times 10 power 26 watt. But as the distance getting further away from the sun, the amount of power that we receive will be lesser. But just keep in mind that there is no losses when the light energy travel outside in the space, because the space do not have any medium. There's no air, so there's no resistance. There's no friction. So in other words, whatever you send out from the sun and whatever you receive on the earth will be the same amount. Okay, only when it start to penetrate through the atmosphere, then the amount of energy will only be filtered. Okay, but why when we get further away from this sun, we get lesser? Because the sun emit the energy in all directions, 360 degrees. Okay, all directions. So try to imagine that the amount of energy is the same, but the average that the total area that is covered become bigger and bigger. Okay, the sphere that contain the energy will become bigger and bigger when it gets further away from the sun. Okay, so the energy density will get lesser for any given point. Okay, yeah? But the total energy is still the same. Okay, this means that when we get further away from the sun, we will receive less amount of energy. Okay, so at the top of the Earth atmosphere, you can see that we talk about the Earth atmosphere, the top of the Earth atmosphere, because we are not able to get the average value when you reach the Earth's surface, because the atmosphere condition is random. It's changing from time to time. Okay, so that we just take the value which is outside the Earth atmosphere, which is around 1,370 watt per square meter. This is the average solar irradiance that reaches the top of the Earth atmosphere before it penetrates through the atmosphere. Okay, and this value we call it as a solar constant. Okay, which is the average value lah, because the solar irradiance oscillation is between 1330 to 1430. The value is changing from 1,330 to 1,430 watt per square meter. This is because the changing in the Earth-Sun distance. Remember that the Earth is evolved around the Sun, but the orbit is not a circle. The orbit is ellipse. So if the orbit is ellipse, it means that some of the time the Earth will be closer to the Sun, and some of the time we will be getting further away from the Sun. Okay, so it changes in terms of distance. So when you have the distance different, the amount of solar irradiance that we receive will be different. Okay, so average is 1,370 once it's outside the Earth atmosphere. So in case you want to do any kind of the solar experiment and you measure that the solar irradiance you receive is more than 1,430, then check your devices. Totally impossible. Okay, we will not get more than this value. Okay, then yes, I need to take the attendant. Then think about this. It's like a electromagnetic wave or a stream of particles. Yeah. Think about it, and then I will post this in Google. See. Okay, go and answer the word on the post over here. Maybe third option, both, or none of the above. Okay, as the attendant, don't take it too seriously. Just make sure that you work for it. electromagnetic wave or stream of particle. Okay, maybe you look on this. This is the properties of wave, where it has the ability to diffract, refract, and interface. They can have the superposition, diffraction, or interference. So you can see that when two light superimpose, they will become very bright. You will double up, the amount of energy will be double up. When they cancel out each other, they will be very dark. When they have this kind of ability, it means that the light is a wave. And in general, light is considered as a wave. Maybe 200 years ago, no one argue about this. Light is definitely a wave. But until I think 100 years ago, Albert Einstein come up with a new theory, say that yes, this light is a wave, but it's also carrying the properties of the particle. Okay, what's meant by properties of particle? The particle should have the momentum and should have the position. Okay, so Einstein made some experiment and proved that light is actually a particle, a package of photon, okay, and the flow of the photon is a wave. So that we can say that light is actually both wave and particle, or maybe they have you can say that light have the properties of both wave and particle. It has the momentum, it has the energy, and it also has ability of the wave or properties of the wave. Okay, but this is not only special for light. Maybe some kind of like electron. Electron also have similar properties. It can be the wave, it can be the particle. Okay. Remember, when you study physics, you learn about the Planck constant. Okay, whichever use the Planck constant, it means that it have to meet this wave and particle, both theory. Okay, so it means that light energy, I can use the equation for wave to explain it. I also can use the equation for particle to explain it. Okay, it fulfill both equation or both mathematical model. Okay, maybe we look on the result. Okay, 35 vote for both. Yes, okay. Okay, then talk about this annual solar irradiation. Okay, keep in mind that we have two terms. One we call it as solar irradiance. Okay, solar irradiance, the unit should be in terms of watt per square meter square. Amount of energy you receive per unit area. This one we call it as a solar irradiance. Okay, amount of power is watt. And you look on this, we call it as solar irradiation. When we talk about the irradiation, it's talk about the energy, total accumulated energy. And this is the annual solar irradiation. It means that total accumulated energy per year. Okay? So the unit should not be in watt anymore, can be in joule, okay, or maybe watt hour. Okay? So in this block, the yellow block represents the annual solar irradiation to the Earth. This is the amount that received on the Earth. I can see this small white box over here. This is the annual energy usage. This is the amount that we need. Okay, and then the yellow one is the amount that we receive on Earth. So maybe just less than 1%. Okay. It means that we receive 1,000 joule of energy from the sun, and we just need 1 joule of energy. Similar, something like this. Okay, and it's even more than the total reserve, fossil fuels reserve, including solid, and also the nuclear reserve on the Earth, including coal, gas, oil, and uranium. It's just this amount. Okay, so in other words, if we can fully utilize the solar radiation, then it's definitely enough to power the entire world. It's totally enough. But maybe you can say that, yes, this annual solar radiation on the Earth is this amount, but 70% is fall on the sea. Okay, and some of them on the mountain, some of them in the jungle. How are you going to harvest everything? And not only human, other organic fauna and flora also need the sunlight. Okay, you cannot harvest all. Okay, fine, then we harvest 0.1%. Very good enough. Okay, maybe we can use the solar energy, we can harvest the solar energy from every building or every road or bridge, something like this. That should be good enough to power the entire city. Okay. Okay, then we talk about the factor affecting solar irradiance received on the Earth's surface in general. There are 4 factors affecting the amount of solar irradiance that we receive. For example, now we are at Kuala Lumpur. Some of you at Penang, Belize. Okay, these 2 locations actually the amount of solar irradiance that we receive will be different. In general, Penang receives more sunlight than Kuala Lumpur. Okay, this just Malaysia, just different location in Malaysia, you will receive a different amount of solar irradiance. Okay, the problem of because of 4. First one is a distance travel through the atmosphere. Okay, why distance travel through the atmosphere will be different? Okay, atmosphere should be have the similar thickness around the world. Okay, similar thickness around 50 kilometer thick. But of course, very hard to define the thickness because the amount of air will be getting lesser and lesser until 0. Okay, I mean the air pressure. Okay, on the Earth's surface, it will be 1 atmosphere. Okay, or 100 kilopascal. And we're getting lesser and lesser when you go higher in terms of altitude. Okay, until you get 0 when you go out to space. But the boundary is not clear, so that we are not able to identify exactly which point is the boundary. Okay, but we can say that the atmosphere has similar thickness around the world. But why the distance traveled through the atmosphere is different? This is just because on the different time. Okay, maybe I can say in this way. Why this sunlight in the morning is much lesser than in the afternoon? Sorry, in the noon. Okay, we know that at noon, 12 p.m., sunlight has the most power, or the solar irradiance is the largest. Why? This is that because the sun is getting closer to us in the sunlight? In the solar noon? No. The sun and the distance between the sun and Earth will be the same for the entire day. But why it has the different amount of sunlight that you receive? In the morning, I feel like, hey, the sunlight is not very strong. It's still okay. I go outside. But in noontime, then something, wow, very, very hot. This is because of the distance traveled through the atmosphere is different. Okay? Why? Okay, maybe I can draw out. Okay, let's say this is the Earth's surface. Okay, and then this is the atmosphere. Assume it's a similar thickness, and you are standing here. Okay, so at the sunlight, at the solar noon. Solar noon is mean that the sun is on your overhead. Okay, the sunlight go through here and reach you. The distance travel is A. I don't know what's the value, I put A. But how about in the morning? The sunlight is to be come from the bottom, right? And then it reach here. When the sunlight is on the bottom, so supposedly, if you're standing here, then you experience night time, so you don't see the light. But at the sunrise, you suddenly see the sun over here. Okay, so the sunlight will go through here, pass through the atmosphere, and reach you, and you see the sun, you see the light. Okay, but the distance traveled here, B, is much longer than the distance traveled in A. Okay, can be 4 times or 5 times longer than A. Maybe in A it just travel 50 kilometers, but in B it will travel 200 kilometers. Okay, so when the distance traveled through the atmosphere is longer, it means that you get more filtered. Atmosphere is like a filter. It will filter out the amount of sunlight received on the Earth surface. Okay, so it makes us in the morning we receive less solar irradiance or receive less sunlight. But in the solar noon, it will be the hottest. Okay, and in the evening or sunset, exactly the same. It's supposedly you will receive the same amount of sunlight as sunrise. But of course, you will say, oh, I feel much hotter than morning. Evening is still much hotter than morning. Why? It's just because the heat that you gain in the daytime still available on the earth. So you feel still very hot. Okay, but in the morning, the heat already fully dissipated to the space, so you not feel anything. Okay, so the distance traveled through the atmosphere is just because of the difference in time. Okay, in the morning, noon, and evening, sunset. Okay, so this thing is not location dependent but time dependent. First point. Second is the ozone layer thickness. Okay, as I say, the atmosphere thickness is 50 kilometer. How thick is ozone layer thickness? The average thickness of the ozone is only 3 mm. Average thickness of the ozone for the entire world is only 3 mm. So it's something like almost meaningless. Okay, the atmosphere thickness is 50 kilometer, and this ozone layer thickness is only 3 mm. Then why this is so important? Okay, because ozone layer will filter out the UV light. Okay, why it will filter out the UV light? So it means that this ozone layer is very thin, so that it's only able to filter out UV light. The X-ray, the visible light, infrared, all nothing to do with the ozone layer. Ozone layer is made from the O3, oxygen, 3 oxygen, they bond together become O3. Okay, and when the UV light hit on this ozone layer, it will break the ozone, break into O2 and one atom oxygen, O2 and O. Initially, ozone is O3. Okay, now it break into O2 and O. And then the UV light gone because the energy from UV light received from this O3 and break into O2 and O. Okay, and then it means that this ozone layer absorbs the entire UV light. Of course, you might have the ozone layer. Some of the case, I think at Antarctica, there's a hole of ozone where there is no ozone at all, so that the UV light can penetrate through the surface. Okay, or maybe we filter out 80% of UV, still have 20% of UV will reach the Earth. Okay, for the entire atmosphere of 50 kilometers, only this ozone able to interact with the UV light. If you pass through the ozone layer, it means that it definitely will reach you already. Okay, so this ozone layer will affect the amount of solar radiation that you receive, because UV also contribute to the solar irradiance. Remember, solar irradiance is totally combination of the X-ray, UV light, radio wave, whatever wave, all the spectrum. We combine all together, we call it a solar irradiance. But of course, not all of them is able to convert to the electricity using photovoltaic panel. Only a certain wavelength of the light or spectrum can be used to generate electricity. Okay, this one we will study later in the photovoltaic chapter. Okay, so this one is just related to UV, second point. And third one is the amount of haze in the air. Amount of haze in the air due to the dust, water vapor, and others. This one I think very direct forward. When you have dust, you have water vapor, the amount of solar irradiance you receive on the Earth will be much lesser. You will filter it out. Okay, and then the last one is the extent of the cloud cover. Okay, extent of cloud cover. Cloudy day, of course, you do not have sunlight because the cloud is too thick. Okay, similar to dust and water vapor. Okay, but normally I can say it this way: cloud cover and dust will filter out visible light. Okay, and water vapor will filter out infrared, which is heat. Okay, so they are slightly different. Okay, but the total amount will be affected by these four. Yeah, just now I talked about the location KL and Kuala Lumpur and Penang. Then it's part under the first point. Okay, the distance traveled through the atmosphere. Okay, this one we will explain more in the chapter part 2, I guess. Okay, because I can say that on every noon, I know that the sun is the highest in the sky, on the sky, but it's not exactly overhead. It can be offset a bit to the north or offset a bit to the south, depends on our latitude. Okay, of course, Penang and Colombo have different latitude, so that the point also different. Okay, so that the distance travel will be different in that way. Okay, okay. I will explain more detail later in the second part of the chapter. Okay, then this is the solar energy reach the Earth's surface. So you can see 100% of the sunlight from the top. How many you actually receive? Only 51%, because you have the cloud. Cloud will absorb some. It will reflect some. Reflect upward you get nothing. Reflect downward you still get something. Okay, and it will scatter. Scatter means something like a change direction. Reflects means that change 90 degree, 180 degree. Okay, it will reflect back. But this scatter is just maybe change in some degree due to the visibility of the air. Okay, and then the atmosphere will also absorb heat. Okay, 19% absorbed by the atmosphere. And then 21% is a direct radiation. And the rest is actually indirect radiation. So this direct radiation is mean that you can see that it's straight line from the sun. So the direction is 100% the same as the direction of the sunlight. But you have still another one, almost half of it. It's called indirect radiation, or we call it diffuse radiation also can. Okay, this is come in different direction, because different cloud reflect it to different direction. Maybe some of the dust atmosphere will reflect into different direction. So I can say that the sunlight that we receive on the Earth have two categories. One is the direct radiation, directly come from sunlight without any change in direction. Second is the indirect or diffuse radiation, come from any other direction, can be any other direction. Okay, but this is not so concentrate, because all of them come from different direction. There is 180 degree that the sunlight can come from. So you will not feel that it's very intense, but only the half of it from direct sunlight, it is very important. And for the photovoltaic panel, for stationary photovoltaic panel, we will take off, we will gain off, because all come from other direction, and then I just put it there, whatever hit on the solar panel, I will receive it, and I generate electricity. But in some of the case, my solar panel is moving, sun tracking solar panel. So how you track the sun? You only track the 21% over here. Okay, diffuse radiation normally you have to ignore, because you have no idea how to track them. You also cannot track one panel. You cannot track all multi-direction. You only can track one direction. So we only always focus on the direct radiation. Okay. So there is a pro and con with the stationary and the solar tracking solar panel. Okay, yeah, this one talk about a little bit about the filter of the atmosphere. Okay, you can see that on the Earth's surface, outside the atmosphere surface, you have X-ray, UV, visible light, infrared, and you also have the microwave and radio wave. But that one is normally will not contribute to the solar energy. Too less, the amount of energy you have too less. No one can feel it. Okay, so I put four types in here: X-ray, UV, visible light, and infrared. And the first layer in the atmosphere is called ionosphere. Okay, it's full of iron. Okay, and X-ray will be completely wiped out in this layer. Okay, remember that X-ray is travel in very short wavelength. So to travel 1 kilometer, it may vibrate more than million times per year. So very fast, the energy gone. So X-ray missing. Okay, UV, visible light, and infrared. although it will filter a bit, but it's still able to go through the first layer. Okay, because the energy that it contains is lesser, so it won't waste too much energy through this layer. And the next layer is ozone. Ozone only able to react with the UV light, as I said just now, because they have a chemical reaction. They break the O3 into O2 and O. Okay, but this layer is very, very thin, just 3 mm. So the visible light and infrared will go through the layer without any filtering. Okay, because there is no chemical reaction, and then the resistance grade by that layer is very less, just 3 mm. Okay, so go through. And below the ozone, we have visible light and infrared. And now, water vapor and carbon dioxide or any other greenhouse gas will filter out the infrared. Infrared is a heat. Okay, so this water vapor and carbon dioxide able to filter out infrared and a little bit of visible light. Because this carbon dioxide and water vapor is a odorless, colorless, do not have any color, fully transparent, so that mostly you will not block any of the visible light, or maybe very less. But why it will block infrared? Okay, this is very subjective. Maybe you can talk about the properties of the greenhouse gas, water vapor, carbon dioxide, or methane gas. We also call it as a greenhouse gas, which can absorb the heat. Okay, this type of gas have the internal vibration, or maybe we can call it as a natural frequency. Okay, so when the sunlight, the infrared have the same frequency as the natural frequency of the molecule of this greenhouse gas, then it will absorb more. Okay, resonance will happen. So it's easy to absorb because the trend, the motion is matched each other. Okay, so it will absorb most of the infrared, but will not absorb visible light in this layer. So whatever we receive mostly will be visible light. Okay, so you can see that we always talk about water vapor and carbon dioxide. It's a bad gases. Carbon dioxide is a greenhouse gas. But if you do not have carbon dioxide, what happens to the infrared? It will reach you directly without any filtering. Okay, in certain extent, carbon dioxide or greenhouse gas is a good gas to filter out the infrared. Okay, but bad thing is it will hold the temperature, it will hold the heat and increase the temperature of the surrounding. So we have the global warming. Okay, so very subjective this thing. Whether it's good or bad, it depends on how much you need. You need a certain amount of heat, but don't too much, but don't too less. Okay, so the amount that receives is the only visible light. And most of the photovoltaic panel will target mostly on the visible light only. Okay. Let's say I hit the X-ray on the visible light. Do you think I'm able to? Okay, sorry. I use the X-ray and shoot it on the photovoltaic panel. Do you think it's able to generate electricity? This photovoltaic panel, it needs to release electron so that it can generate electricity. Okay, so whether it can release the electron depends on how much energy is received from the sunlight. The higher the energy, the easier it can release the electron. Okay, now electron is actually held by the semiconductor. The semiconductor hold the electron. So you need the sunlight need to give the energy to the electron so that it can break the bond from the semiconductor and it can travel through the outside circuit and produce electricity. Okay, in other words, X-ray and UV light have the highest energy than visible light. So whichever visible light can break the bond of the electron, X-ray and UV also able to do that. Okay, but you have excessive energy. You just need 100 joule of energy, but now the X-ray support 1000 joule of energy. So where the 900 joule of energy go? It will become heat. Okay, in other words, if you use X-ray or UV light on your solar panel, yes, you're still able to generate electricity, but you produce heat and then you reduce the efficiency of the solar panel. Okay. But of course, you can see that visible light, and after visible light is infrared. If I use the infrared then shoot on the solar panel, then no electricity come out. Okay, because infrared do not have enough energy to break the bond of the electron. Okay, higher is okay, but lower not okay. But higher will generate heat. Okay, so of course, ngam is the best lah. Visible light is ngam. Okay. So advantage of solar energy. All chemical and radioactive polluting byproduct of the thermonuclear reaction remain high on the sun, which only pure radiant energy reaches the Earth. Actually, the thermonuclear fusion is it produces very high pollution. Okay, or maybe you can say it's toxic fusion, like a nuclear fusion. All is very, very dangerous and toxic. But now we don't care; it just happened on the Earth. Sorry, what happened in the sun, but not radiate to the Earth. Whatever we receive is any pure and green energy from the sun. Okay, so this is a good thing about solar energy. Totally green. Although the process is similar to the concept of the electric car. Okay, electric car is very green, but whenever you produce electricity, it's very highly pollution. But you put it behind outside the city, then okay lah, similar. Now the fusion process is very, very toxic, but I put it on the sun. I just receive the pure energy, green energy from the sun. Okay. Energy reaching the Earth is incredible. By one calculation, 30 days of the sunshine striking the Earth has the energy equivalent to the total of all planet fossil fuels, both used and unused. Okay, just 1 month, the energy that we get is equivalent to all the planet fossil fuels, all the planet fossil fuels that we have on the Earth. So we can say that the potential is very, very huge. This sun is sufficient fuels remain from the sun to continue radiating peacefully for another 5 billion years. Of course, this is just some kind of prediction. They just guess according to the calculation. But how they count, I don't know, because the sun is quite far from Earth. There's too many assumptions that they have made in their calculation. So if this is true, 5 billion is still very, very long. Now we're worried about COVID more than this, whether the sun can continue to radiate peacefully. Okay? Maybe the Korea and China are making the artificial sun for these purposes. Possible. Okay. Disadvantage of solar energy, sun does not shine consistently. Okay. Consistently, I think refer to the atmospheric condition. Yet later you have clouds, later you have dust. Okay. You notice that in Beijing, China, they not really use the solar panel. They use wind most of the time. Okay, because the dust content in their air is very, very high. Okay, they have a lot of dust in the air, so they are very high. I think the BMI they call it. Okay, so that the visibility on the light or on the air is very less. So that the sunlight can reach the surface is also very less. So if you use a solar panel in Beijing, then you make the output power very, very low. Okay, so that they focus more on the wind energy rather than solar energy. By Malaysia, yes, we always have a very clear sky. So solar energy have very huge potential in Malaysia. And second problem, solar energy is a diffuse sources. Diffuse sources mean that it's not concentrated. Diffuse everywhere. Okay. Yes, I know that solar have the energy, but you're standing on you're exposed to the sun. Are you really able to feel anything from the sun? You just feel the light, just a little bit heat, but it won't kill you. Okay, because the energy content is very less. The energy density very less. Yes, if you accumulate the area of the 1 kilometer square, then you can get a lot. But if you get a small area, you will get very less. Different from uranium. One small pieces already can kill you. Okay, but this one, we call it very diffuse. You need to accumulate everything. Okay. And the third disadvantage is that to address by approaching the problem through the collection, how are we going to collect this diffuse solar energy? Any effective way to collect it? Secondly, after we collect, how we convert it to the useful energy, such as electricity. Okay, it can be many methods, but now mostly you focus on the photovoltaic technique. Okay, the last one, after we do the conversion, how we store it? Are you able to store the light energy? Mostly not, but if you convert to electricity, we are able to store the electricity. Okay, these are the problems that we need to consider, like how to increase the efficiency of all of them. Okay, then we talk about the radiation, type of radiation, solar radiation. We have beam radiation, diffuse radiation, and total radiation. So beam radiation is what I said just now. We call it as a direct radiation, which is directly come from the sunlight without any change in direction. We call beam radiation. Okay. Okay. Or we also call it as a sunshine, and these radiation are very intense and have harmful effect if they fall straight into our eyes. Okay, so we call it direct radiation. Remember, there's no change in direction. And second one, we call it as a diffuse radiation. This is because when the solar ray pass through cloud, they get diffused because the cloud contain suspended particle, water vapor, and gas. So the direction of the sunlight will change. Okay, so we make it diffuse because the change of direction is not the same for every sun ray. It will be random. Okay, so scatter, refract due to the which the energy is very much reduced. So we call it this diffuse radiation. Okay, and we last one called total radiation. I think you should be able to understand. Total radiation is the diffuse radiation plus the direct radiation. We call it as a total radiation. It's a sum of beam radiation and diffuse radiation, and they are also called as a global radiation. Total solar energy falling on per unit area on the part of Earth called total radiation, and it's measured of watt per meter square. Okay lah. This is just a measurement. Normally we will use the pyrometer to measure solar radiation, and the unit give will be watt per square meter. And how we measure the solar radiation? Before that, what principle can be used? So in general, we have three principles to measure solar radiation here: thermocouple for photovoltaics and solar concentration. But the last one, solar concentration, only give you the indicator whether you have sunlight or you don't have sunlight. Okay, but the first and second will give you the exact value of the solar radiation. Okay, first one is the principle of thermocouple or thermopillar. Okay, this one we call thermopillar, or the concept here we call it seeback effect. Okay, you can see that if I connect two different metal together and one is exposed to the heat, then it will produce the voltage. Okay, or electromotive force in milliwatt. Why I want to mention it in milliwatt? Because it's actually very roughly. Okay, and this EMF produced is proportional to the temperature and proportional to the solar irradiance you receive. Okay, the higher the solar irradiance, the higher the temperature, the higher the voltage that you produce over here. Okay, this seeback effect happen because whenever you supply heat to any metal, you have the moving electron. Because the electron receive energy, then it can move. Okay, but different matter have the different effect on the heat. Some of them will generate more electron, some of them will generate less electron. But if I compare two different matter, then I can see the difference in terms of electron flow. Okay, then this will give you the potential difference in terms of voltage. Okay, if I use both as the same material, then yes, both have the flow of electron, but both have the same amount of flow electron. So in other words, the potential difference in these 2 points is still the same. Okay, because you want to find the difference between these 2 points, you only can get the voltage. Voltage is referred to potential difference. Now it's still the same. Then you get nothing, you get zero. So must be different method. Okay. So this is one of the method we can use to identify or to measure the solar irradiance. Second method is the photovoltaic principle. This one is, I think everyone of you are clear about this. We have sunlight, it will generate electricity. The more the sunlight, the higher the electricity that produced. Okay, photovoltaics can be used to measure the intensity of the solar radiation. When solar ray fall on the silicon cell is a main material for photovoltaic panel. Of course, not all the photovoltaic panel made from silicon, but silicon is the most cost-effective solar cell. Okay, because silicon is very cheap. We still have many types of the photovoltaic panel, but silicon cell is a widely used solar cell. Okay, when solar rays fall on a silicon cell, electricity is produced, and hence radiation measurement instrument can be calibrated directly with watt per square meter to know the value of solar content. These are 2 methods. One we use the photovoltaic principle, one we use the thermopyler principle. And last one, we call it as a principle of solar concentration. You can see that you have the ball act as a convex lens. So convex lens will focus all the sunlight into one single point. So that single point will have the high temperature until it's able to burn the paper. You put the paper at bottom of the convex lens. Okay, so in the paper they will mark the time. Okay, so you can see that if from this paper, I can see that from what time to what time I have the solar, I have sunlight. From what time to what time I don't have sunlight, based on where it's burned. So if the paper burns, it means that you have the sunlight. If the paper not yet burned, it means that the amount of sunlight is not enough. Okay, so that it only can tell you whether I have sunlight or I don't have sunlight. But of course, they have a threshold value for it. At what temperature you're able to burn it, at what solar irradiance you're able to burn it. Okay, first, they set the target, the threshold value at 120 watt per square meter. If the value is more than 120 watt per square meter, then consider as a sunlight, and it should burn the paper. But of course, this method is not accurate enough because it will affected by the environment. Remember that you want to burn something, you need oxygen, you need heat, and you need temperature. You need temperature. Okay, so the temperature of surrounding will greatly affect the reading over here. Maybe at a colder climate, then you will get much lesser point getting burned. Not because of the low solar irradiance, but just because the surrounding is too cold, so that the paper cannot be burned. Okay, so this method I think not really in use anymore. This is an old method. Because now photovoltaic panel is so cheap, and then the sensor also can be very, very cheap already. So we don't need to use this method anymore. Okay. And the solar radiation measurement instrument, we have 3 different types: pyrometer, pyrometer, and sunshine recorder. We look on the first one, pyrometer, which is the mostly used. Something like UFO. Okay, it's measure total or diffuse radiation. Okay, this white plate is called pyrometer. It's used to measure the solar irradiance. And this one also similar case, but it's the upgrade version of the pyrometer. We call it as a epi pyrometer. You can see that there's a black ring over here. Okay, and this device only measure the diffuse radiation. Okay, remember this is open so that you absorb sunlight from all directions. So I can say that the measurement refer to the total radiation. Okay, but this one you can see that there's a black ring. Okay, so you have to set the black ring so that it blocks the direct sunlight. Okay, so whatever you receive on the pyrometer is only diffuse radiation. So how are you going to set the black ring? So you set the black ring as long as the shadow of the black ring fall on the sensor head, then it means that the reading that you get is only diffuse radiation. Very simple, right? As long as you see the shadow block on it, then whatever you measure is a diffuse radiation. And this is open so that you will measure everything: diffuse radiation, direct radiation, everything together. Okay. Okay, this is the schematic diagram of the pyrometer over here. So you can see that first you have two layers of dome or glass dome. Okay. Why do you have a color of here? Actually, this pyrometer have a few standards. Okay, some have one layer of glass dome, some have two layers of glass dome. Depends on what is your requirement, how accurate you need for the measurement. Okay, the function of glass dome over here is to maintain the temperature inside the sensor. Remember that outside you have the heat. Maybe the temperature outside is low. Okay, so these glasses will try to minimize the effect of outside environment to the detector. Okay, maybe the detector is made from thermometer. This thermometer is the measurement of the temperature change. So if the outside have a strong wind, then your detector become not accurate enough. So we need a layer of glass. But in some of the case, two layers of glass will be much better. It will be more consistent. Something like, why our roof we have one layer, why we still need the ceiling? We try to reduce the temperature change in the room. So we need a ceiling. Okay, of course we have to make it nicer also, but in terms of engineering knowledge, we try to put it to avoid the sunlight to hit it faster. Okay, so we need a two layer of glass dome just to protect the detector from the heat transfer through conduction. Okay, and then you can see that this has the sun shield. Yeah, okay, you can see that sun shield over here, the white plate over here. First, white is white. Why not put it other color? Because this plate is connected to the sensor. Okay, if you put it black, in other words, it will increase the temperature of the sensor. The heat will travel through the plate and then through the conduction to the sensor. So it increases the temperature. So it must be white. Okay, so that the heat will not travel through into the sensor easily. When it's white, it will not absorb heat, so it won't too hot. And you can see the angle of the shape, maybe 120 degrees outward. So the whatever sunlight hit on it will not reflect to the sensor. Okay. And then next one, I haven't talked about the function of this. This one we call it as a sun shield. Okay. Actually, it's to protect the refraction from the ground. You can see that the sunlight from above will hit the ground and reflect to the sensor. But if I have the plate over here, whatever reflects from the ground will hit on the bottom part of the plate. Okay, so it will not reach the sensor. So this is the main function of this sun shield. But of course, they have the design of this shape and they have design of this color. Okay, yeah, I think time's up already. I think we should stop here. Okay, we will continue on our next classes. Any question before we dismiss?
No questions, sir.
Okay, that should be very general. Okay, then I think we can stop here now. Thank you very much and see you next classes. Bye bye.
Thank you, sir.
Thank you, sir.